Welcome to the Greek Ship Corrosion channel. My name is eحتشام Zade. I'm a researcher in the field of corrosion and protection of materials. Please find more information about this channel in the description below. Chapter 1, Section 3. Basics of electrochemical corrosion. The main variables in wet corrosion and corrosion product formation on iron are discussed in this section using this reference. What is wet corrosion? Wet corrosion occurs in the presence of a liquid containing ions that is called electrolyte. Problems with wet corrosion attacks in stainless steel occur in mineral acids, processed solutions, seawater, and other chloride-containing media. Examples of wet corrosion forms are crevice corrosion and erosion corrosion. In this figure, the rusting of iron in the presence of humidity and oxygen is illustrated. Oxygen demands electrons for reduction and produces water or hydroxyl anion. Iron provides electrons for reduction of oxygen and is corroded. This is anodic site and this is cathodic site. This is electrolyte and this is the path of electron transfer. Oxygen reduction in acidic solutions is based on this reaction, and oxygen reduction in neutral solutions is based on the second reaction. pH, a major variable in corrosion. Reminder, although oxidation is a chemical process that involves the loss of electrons, such as Fe equals Fe2 plus 2 electrons, we should not use the word oxidation instead of corrosion, as the word oxidation may bring to mind that corrosion requires oxygen, whereas corrosion can also occur in the absence of oxygen. It should be noted that iron needs both oxygen and humidity for rusting, as shown in the previous slide. The first state, consider the conditions in the absence of oxygen, called deaerated environment. For providing a deaerated environment, oxygen is excluded by nitrogen gas purging and overblanket. Corrosion occurs when the electron demand from the components in the environment overcomes the metal electronegativity and forces the metal to provide the desired electrons for reduction, and as a result the metal loses electrons and is corroded. The metal passes from the metallic state to ions of valence M in the solution with the evolution of hydrogen gas and electrons transfer from M to H+. Cathodic reaction in a deaerated environment that supports corrosion reaction is 2H plus 2 electrons produces hydrogen gas. Anodic reaction, which involves metal corrosion, is M converts to M plus M electrons. The overall reactions as shown below are in acidic solutions and neutral solutions respectively. M plus MH plus react to produce Mn plus M divided by 2 mole of hydrogen gas. M plus M mole of water produce Mn plus M mole of hydroxyl plus M divided by 2 moles of hydrogen gas. The first reaction is at pH lower than 7. The second one is at pH greater than or equal to 7. Since the metal is an electron conductor, it supports the electron transfer, allowing the two processes to occur at separate sites on the metal surface. Cathode, the site that reduction occurs on its surface. Anode, the site that oxidation occurs on its surface. Uniform corrosion with pH as a major variable in deaerated conditions. Left figure, in which pH is lower than 7, illustrates that H+ cations are reduced and hydrogen gas is produced and evoluted. In the right figure, in which pH is greater than or equal to 7, water molecules are reduced and produce hydrogen gas and hydroxyl anions. 4 bases are observed in all cases: cathode, anode, path for ion transfer, path for electron transfer. Here is cathode, here is anode, here is the metal that provides the path for electron transfer, and here is the environment or the solution that provides the path for ion transfer. Uniform corrosion with pH and dissolved oxygen as variables. The second state. Consider the conditions in the presence of oxygen called aerated environment that is common in industries. When dissolved oxygen is present in the solution, usually in contact with air, the following reactions occur in addition to those just considered in the deaerated environment. M plus M divided by 4 moles of oxygen plus MH plus react to produce Mn plus M divided by 2 moles of water at pH lower than 7. And if the pH is greater than or equal to 7, M plus M divided by 4 moles of oxygen plus M divided by 2 moles of water react to produce Mn plus M moles of hydroxide plus M plus MH plus that produce Mn plus M divided by 2 moles of hydrogen gas. And if pH is greater than or equal to 7, M plus M moles of water react to produce Mn plus M moles of hydroxyl and M divided by 2 moles of hydrogen gas. In the presence of oxygen, the number of oxidizing agents and oxidizing power of the environment is increased. In other words, in addition to hydrogen evolution reaction, oxygen reduction occurs. The dominant cathodic reactions are observed here. Oxygen is reduced in the acidic solution and water is produced. In the right figure, oxygen is reduced in neutral solution and hydroxyl is produced. In addition to these reactions, hydrogen evolution reaction occurs. That is, 2H plus 2 electrons produce hydrogen gas. Corrosion product formation on iron under aerated conditions in the temperature lower than about 771 Kelvin. Rusting of iron is an example of corrosion product formation at pH greater than 4 approximately, and under aerated conditions a layer of black oxide Fe3O4 and possibly FeOH2 forms in contact with the iron substrate. In the presence of dissolved oxygen, an outer layer of red oxide Fe2O3 or FeOOH forms. The sequence of the phases are shown in this figure. Iron substrate, black oxide Fe3O4, red oxide Fe2O3, aqueous environment, gaseous environment. O to Fe ratio in hematite is 3:2, 1.5, and in magnetite is 4:3, 1.3. During the conversion of magnetite to hematite, the oxidation state of iron increases from 2 to 3. Oxidation reaction of magnetite is as the following: 4 moles of Fe3O4 in solid state plus 1 mole of oxygen gas react and 6 mole of hematite is produced. Corrosion product formation of iron. Anodic reaction is Fe converts to Fe2 plus electrons, and the overall reaction are Fe plus half a mole of oxygen plus 2H plus produce Fe2 plus or ferrous cations plus water, or 4 moles of Fe3O4 plus oxygen produce 6 moles of hematite. The rate of corrosion depends on the factors influencing the kinetic mechanisms of the several processes involved in the transport of ions from metal to solution and in the supporting cathodic reactions. Corrosion product formation on iron under aerated conditions in the temperature higher than about 771 Kelvin. Higher temperatures speed up the rusting process by increasing the kinetic energy of the particles involved, leading to more frequent collisions and a faster reaction rate. This is why iron objects rust faster in hot and humid environments compared to cooler, drier ones. The most oxygen-rich compound is found at the scale-gas interface, and the most metal-rich compound at the metal-scale interface. Here is metal-scale interface, and here is the scale-gas interface. For Fe above about 560 Celsius or 833 Kelvin, the phase sequence is Fe, FeO, Fe3O4, Fe2O3, O2. Wostite is porous and cannot protect the substrate. It is an antiferromagnetic compound and is not stable thermodynamically under the temperature of about 560 Celsius or 833 Kelvin and decomposes to magnetite as the following reaction. 4 moles of wostite convert to 1 mole magnetite plus 1 mole of iron. Thank you for your time. If you like to challenge yourself, please comment down below. What is the hematite structure formed on iron at room temperature? Alpha-hematite or gamma-hematite? Zhang et al. In 2021 showed stages of magnetite during non-isothermal oxidation. At temperatures below 500 Celsius, surface oxidation occurs. And here are the reactions. That is stage number 1. At temperatures above 600 Celsius, further oxidation occurs. And here are the reactions. That is stage 2.